know who that is.
Yippee. Okay, so it wants me to admit some people, but some people just get instant in. Right, right.
Yeah, I don't know why it doesn't.
Okay. Okay, so I'll give it like a minute. Join, is that okay?
Yeah, we could give it a minute. There was 21 people registered for online.
Okay, sweet.
I don't know. That doesn't mean they'll all show.
It's good attendance.
Yeah, I kept sending like reminders to the list of Oreos.
Well, for online and in person, we're gonna give it like a minute for people to join, and then we'll go ahead and get started.
Mhm.
My bad.
I don't know if you meant to do that. So
My bad. Okay. Okay, let me share my screen and then we should be good to start.
I like how most of the campuses where I'm sure. You could also minimize it if you want.
Oh, I can?
Yeah, you can press that or the one next to it.
Oh, okay, that's so much better. Yeah. Okay. Sweet. Okay, so we're gonna go ahead and get started with the workshop. Let me actually make sure that chat is maybe okay. I think I'm good. Thank you. Okay, let me pull chat over there just in case it does go off. So if for my people online, if you can't hear me or anything, just let me know. And for both online and in person, if you guys have any questions at any point during the presentation, just let me know. So this one is going to be a little more general than if you've gone to like SI or peer tutoring before. We're really going to focus on like study skills and how to be successful in organic chemistry, especially going into these next few chapters, because from my understanding, you guys should be getting into the portion where you're talking about reactions, mechanisms, that sort of stuff. Yeah. Okay, sweet. So I'm definitely going to have some tips and tricks for those because I know those are kind of getting into the more intimidating chapters when it comes to Orgo. So I'll definitely give some recommendations. Oh my God, my computer hates me. Okay. So my name's Becky, and I'm a graduate assistant here for SART. So, for a bit of context, I was an Orgo tutor for the last 2.5 years. So, I've been in the game for a while. I'm currently getting my master's in chemistry, but I did get my bachelor's in forensic biochemistry. So, I was really excited when you said forensics. I was like, activated like a sleeper agent. So, yes, yes. So, that's my qualifications. Our agenda for today is we're going to start off with textbook tips because I'm pretty sure we all have the same textbook, which is like the fifth edition, Dr. Klein, Understanding Organic Chemistry. Hasn't changed in forever. And I don't know about you guys, but it's a little bit intimidating. If you've ever tried to read it cover to cover, which I have, I don't recommend. And then we're talk about managing the mechanisms for the reactions. And then lastly, we're going to talk about how to remember all of the reagents. Because I know that's kind of getting ahead. There's going to be quite a few reagents that you're going to need to know going into these like last two chunks of the class. So starting off with our textbook tips, the most common thing I hear people in organic chemistry say is, I'm going to read the whole book. Guys, we've all seen the book. Have you seen the physical copy of the book? I think it's literally could be a weapon. Okay, it's giant. This is my reaction whenever someone says they're going to read the whole textbook. Please. cut cameras, don't do it. Basically, let's do some quick math. In just the organic one section, 634 pages. Yeah. It's about 140 problems per chapter. Yeah. So when people are like, I'm gonna do every problem in the textbook and then I'll what you're gonna do is give yourself burnout, is what you're actually gonna do. So that is not something I would recommend. So how can we make the most of when we're studying the textbook? I'm so glad you asked. Starting with the skill builders. So you can tell they're a skill builder because one, they'll say it, and two, they have this like funky little bicycle next to them. And so these are sections between the text that are going to break it down into smaller chunks. And the reason I really like this is because if you are reading the textbook, the minute you're introduced to any new information, it's going to give you a little skill builder to directly practice that thing that it just taught you. So I think that's really beneficial to make sure you're learning every individual step before you try and attempt like any of like the larger synthesis problems. And so the other good thing that I like about these is that the difficulty increases over time. So what I mean by that is when you scroll in, usually you see problems A through D or A through Z, more like in chemistry. Um, problem. Please don't do every problem. So basically, what I mean by that is A is going to be the easiest one in the problem set, and Z is going to be the hardest. So why go through and do every single one? So what I usually did was I would start at A. If I can do that, skip to the middle. Go for like G or something. If you can solve that one too, start skipping down to the really low level ones, or the really high level ones that are lower on the list. And then you can kind of play around with that. There's no reason you should be doing 50 problems for every single skill builder. That's just unrealistic. You're going to burn yourself out, right? So that's what I mean when you can self-test to determine your level of understanding, see where you're operating on that list of problems, and that's really going to help you know what to focus in on and make it more manageable. Does that make sense? Sweet. And if you have any questions online, you can either unmute, put it in the chat, whatever's easiest. Okay. So the other important one to practice is practicing ACS style questions. So I'm sure pretty much all of you have probably heard from your professors at this point that the questions on your final are going to be ACS styled. What does that mean? That basically means maybe good, maybe a little nervous. All of the questions on the final are going to be multiple choice. So maybe good news. Um, so means that basically they're multiple choice, but you're not taking the actual ACS because the actual ACS includes Orgo 1 and Orgo 2. So if you take Orgo 2, you'll take the actual ACS that year. So ACS style, guess where they're pulling those ACS style question from? Your textbook. At the end of every single chapter in your textbook, there's a section labeled ACS style problems. And so this is really helpful because one of the things I found that students got tripped up on a lot is the phrasing of the multiple choice questions. So if you're getting tripped up on how they're phrasing the questions, the way they're asking it, would really recommend that you go and scroll to the bottom and find those ACS style questions for those chapters. Usually they'll have like 5 to 6 per chapter. And I'm telling you, they're not creative. They'll reuse the problems, the professors. So make sure you check those out. So any questions about those or about what ACS style means? Sweet. So one thing I was gonna say is don't you hate practicing and you don't know how well you're doing? I do. Well, every problem comes with an in-depth explanation, and I don't think enough people know that. If you buy the online version, or if you're like renting the online version of the textbook, I think even a physical copy has it too. But basically, whenever you're doing a problem, you see how it's underlined and like green? It's because it's a hyperlink. So if you click on the number, it takes you to like the back of the textbook. And the back of the textbook has in-depth, step-by-step explanations of how to solve every single problem in the textbook. So just throwing that out there, all you got to do is just click that hyperlink and you can tell exactly how you're doing when you're practicing at home. So I really like that because the instant feedback is super helpful because there's no point practicing and not really knowing whether you're improving or where you're at. So, any questions about that? Sweet. I feel like a lot of people don't know it. They're pretty sneaky with the hyperlinks. Okay. And then get to one of the last recommendations I have. I'm going to close chat for now just so we can see the absolute glory of this map here. But especially if you get to these upcoming chapters, the textbook is full of figures and concept maps that you can use to study. So here's an example of said concept map. Doesn't that look really scary? It looks super intimidating. You'll get to a point where you'll see this and you'll be like, I see the connections. It's all making sense now. So basically, how I would recommend studying with these webs is don't just ever look at it right now every time I peek back at it. So I would recommend erasing these steps in the mechanism and fill them in yourself. So these parts here, and maybe I'll use my mouse because that might be easier. You can erase these parts that are on the line to test if you remember the reagents, or you can erase the final product and fill that in. And I would recommend you do practice doing both because some questions are going to be styled as what's the reagent, and some questions are going to be styled as what's the product. So it's a really, really good summary of every single new reagent you've learned in that chapter. And so these are the webs. And then the next thing is going to be figure 7.18, which we will go into an in-depth explanation in a moment because it warrants its own slide. So basically, the more you're actively interacting with what you're reading, the better you're going to be able to recall those important details. A lot of people, when they study the textbook, they're just reading the content passively. And that's fine, but at the same time, you're not really retaining that information that well. It's like on a lecture and the professor just kind of speaks at you the whole time. Like, sure, you heard what they were saying, but like, could you replicate it? Probably not, you know? So the more times you're actively interacting, the stronger those connections are going to be in your brain. So, any questions? Sweet. Oh, oh my God, where did my mouse go? This is not the only concept map. So this map for, I believe, those reagents, it's given chapter 8, I believe. A concept map for chapter 8. Um, but there's one for chapters 7, 8, 9. Basically, your guys are going into the portion of the course, which is like reagent, product, reagent, product. It's very cause and effect. So this is like a basic summary of every single new product, every single new reagent that you're learning in all those chapters. So each chapter will have its own concept map. And like I said, they look scary right now, but they're lifesavers because that saves you from having to reread the whole chapter again and again. Because you're like, oh, I don't really remember what BR2 does. Then you can just like scroll to the concept map at the very end and be like, oh, that's what BR2 does. So I would highly recommend. Yeah, I know there's a lot up here. You don't freak yourself out. You'll learn all these mean eventually. So let's get into managing mechanisms. So all mechanisms, they look really scary, but they're built on a very few amount of building blocks. And so what I mean by that is basically we're going to need to know some very important definitions first. So I don't know how far y'all have gotten into chapter 6 and chapter 7. I feel like chapter 6 is really skipped over by a lot of professors. They kind of like speed run that one a little bit, which is crazy because that's where you're starting to get those foundational definitions and building blocks that are going to be super important going into chapter 7. So a lot of people, like back when I tutored for it, they would be like, yeah, reach out to this girl. We're not testing you on that. And everybody would be like, great, don't have to read it. Those were all the definitions that were vital for understanding the next few chapters. So I would not recommend skipping over that one. So when we more into content stuff, some two very important definitions are going to be your nucleophiles, which we have a picture of our nucleophiles, and our electrophiles, which we have our electrophiles as well. So, shocker, chemists are really creative at naming things. So if you forget what is which, you can kind of just break down the names. So the first part, nucleo for nucleus, electro for electron, and we have the suffix file. What does that suffix mean? Yes, attract. So we have nucleus lover and electro lover. And so the nucleus lover is going to have areas of negative or partial negative charges, and they're going to be attracted to positive charges or protons. So think of it as like a magnet. It has a negative charge, so why does it want to go somewhere with a negative charge? Opposites attract, it's going to want to go somewhere with a positive charge. And so are the same thing, but inverse. So they already have the positive charge. They're going to be attracted to areas of negative charge. And I also did partial charges. Have you guys gone over partial charges yet? Maybe. So it's like might not be a formal charge on a molecule. If you have an atom like oxygen, it's a bully. It's taking all of those electrons. So even though it doesn't have like a full charge, it's implied that there's a partial negative on it. Yeah. So these are going to be your foundational definitions of positive, negative, opposite attract. Question?
So like the partial charge is gonna be on the oxygen and the partial positive charge is gonna be on the carbon.
Yes. So this could be an example where instead of having a full negative, you could have had like a double bond on that oxygen. I believe that's like a ketone. So ketones through resonance, they have like partial charges. You could have a partial negative on the oxygen and a partial positive on the carbon that's bonded to that oxygen. Yeah, good point. Are people online? Are we doing okay? Let me take okay, we got some stuff in the chat. Where's my mouse? Please. Check.
So like you don't have that positive organization. They have like it's third acid.
Okay, so important definitions. So we got our foundational players, our nucleophiles and our electrophiles. But some other important definitions are going to be now what do we do with them? Right? So the first one we have is a nucleophilic attack. And this is going to be when a nucleophile attacks an electrophile. And what by attack is basically it's going to use its its electrons to interact with that electrophile to form a bond between them. Does that make sense? Sweet. So what's the group? Yeah, this one is like all in the name. They really weren't creative with this one. You're losing a group. You're losing an atom. And usually it's going to be a heteroatom. So what we mean by that is like oxygen, or more commonly, the halides. So like chlorine, bromine. They love just up and leaving for no good reason. So the next one we have is a proton transfer. And so I see a lot of students get confused with this one because it has proton in the name. And you're like, well, that's weird because we don't really draw out protons, right? We usually draw electrons and electron movement. So when we say proton, what we're usually actually saying is the movement of a hydrogen. Because if you think about it, hydrogens only have one electron, one proton. So if they lose that electron, they're basically just kind of like a proton. So usually proton transfer is talking about those hydrogens instead. And then the last have is rearrangement. Sorry, rearrangement, and that's going to be the shifting or moving of something that already exists on that molecule. So that's going to be the big kicker. You're not introducing anything new. It's going to be like I don't know the difference. Intermolecular, like within the molecule. It's not interacting with other things. So these are going to be the main four. They call them arrow pushing methods. Have you guys gone over these, or was it something that they kind of skipped over? Yes. Exactly. You tend to like go real fast past it because they kind of assume that you'll pick it up as you go. But these are like really, really important because once you get into like the SN2, E2 reactions, they'll be going through the mechanisms. They'll be like, yes, and then we have a nucleophilic attack followed by a proton transfer. And everybody is like, whoa, wait up, what do those words even mean? And so that goes back to the end of chapter 6 and these 4 arrow pushing methods. Any questions about these?
Go over that piece, I think.
Attack would be like if something had a lot of like electrons. So if we go, I don't know if the PowerPoint will let me go back to the last slide. It does. So you see this oxygen here. It has a full negative charge, so it has extra electrons, and it might interact with something like what we see on the right, um, which is a carbocation. And so it can use its electrons to form a bond between itself and that carbocation. So we call that a nucleophilic attack.
So it's just donating its electrons to that, or
It's not just handing them over. It's like forming a bond between a nucleophile and an electrophile. And that'll be a really common step in the substitution reactions, which I think you guys are about to get into eventually.
yeah.
Yes. Very big step in the substitution reactions are the nucleophilic attacks. Sweet.
As far as like, is there like a picture of like a rearrangement? I know it says there in the definition, but as far as like the shifting and moving something.
Put images of them in later. Activity later. I think the activity might have images, and so we might get to see a few examples of that. It's been a hot second since I gave this presentation, so if I'm a little rusty, forgive me. So one of my tips is whenever you're looking at a new mechanism, try and determine which arrow pushing methods were used. And what I mean by that is if you're going through the textbook or if the professor's going over an example, there are like a lot of different steps with a bunch of arrows drawn out. And they're not really going to be separating those steps a bunch. It'll just be like one long chain. So to try and break it up, you can look at it chunk by chunk and be like, okay, so I see this first arrow we drew was a proton transfer. The next arrow we drew, that looks like a nucleophilic attack. And so once you start to recognize those patterns, what you'll see is they're actually pretty repetitive. Because for now, at the level of organic 1, you're really only using like those 4 tools in your toolbox. So it's got to be some combo of those. So definitely that'll help break down the mechanisms a little bit and make them a little bit more manageable. Sweet. So now to part 3, which is going to be, we just saw that concept map. How am I supposed to remember all these reagents? Very valid crash out. So this is where we go to, oh my gosh, if you take anything away from this, figure 7.18, please, is going to be quite possibly the most important graphic in the entire textbook in organic or an inorganic one. So basically what you guys introduced to, I'm not sure how far you've gotten into chapter 7 yet. Have you started SN2, E2 yet?
We kind of like,
So
not going into detail, but he was like saying like, oh, this is like an S1.
Okay.
S1.
Let's see what they're saying in chat. Let me scroll down a little bit. No, not yet. Quite understand what this chart is saying just yet. Don't be scared. It's likely that you're just getting like a little sneak peek preview of what you're going to be covering in probably the next week, judging by where you guys are at. But basically, breaking it down is when you're looking at these reactions and reagents that you're seeing in chapter 7, you're going to have options of what mechanism can happen. So that's where we're seeing these E2, SN2, SN1, E1. And you have to determine which reaction is going to happen under the conditions that you're given. Does that make sense? So you have like different choices and you got to figure out which one is going to happen. So before approach a problem, you need to know what reaction will occur. And so figure 7.18 is basically summarizing what reactions occur under what conditions. It basically summarizes the entirety of chapter 7. So what I mean by that is if you know that you have a strong base and a weak nucleophile, and what you're looking at is primary substituted, you know that you're going to have an E2 reaction. So if you're wondering what these ones mean, where it's kind of uneven split, that's basically telling you your SN2 is going to be your major product, your E2 is going to be your minor product. So that's why I really, really love this graphic from the textbook because it'll show you major, it'll show you minor, what conditions, how many substituted it needs to be. And so this is basically going to be probably the majority of what your next test is going to be on, will be this stuff. So if it still looks intimidating, don't worry, because I do believe the next few slides is breaking down how to read this visual step by step. And don't worry, you don't have to write out this whole thing because it is called figure 7.18 in the textbook. So you can just control F that to find it later. So yeah, if nobody got me, I know figure 7.18 got me. But how do I know if the reagent is a strong base or a nucleophile? I'm so glad you asked because there's another figure for that, and it's figure 7.17. So 7.17 will literally summarize every single reagent that you might see in chapter 7, and it comprehensively breaks down the different categories of reagents you might come across. And so one of the reasons I really, really like this one is because the way it's organized, it makes it easier to start seeing patterns between them. So, for example, what's the pattern that we recognize between strong base, strong nucleophile and weak base, weak nucleophile?
Charge.
The charges, great. Anything else we notice about strong base, strong nuke, weak base, weak nuke?
Which two, the strong base, strong nucleus.
Well, they gained of the weak base and weak nuke gained a proton or
Exactly. They gain proton. They're the exact same reagents. You just slapped an extra hydrogen on it and now it's weak. It's a weak base, weak nucleophile. What do we notice about weak bases, strong nucleophiles? What's like a common denominator between those? Between this one
Between the 2 and 3 or,
or just category 3?
oh. What are we comparing to? Or,
It's just in that category alone. What do you notice about the ones in that category? Like atoms like iodine, bromine, chlorine. Is there a pattern between those? Do we remember pulling from our Chem 1 knowledge? Let's see if Chat can help. I'm going on the right track of like trying to classify those atoms. Ooh, strong nucleophile, large atom size. Ooh, I like that we're thinking of atom size. So kind of following the trend of the atoms themselves, what we're seeing is iodine, bromine, chlorine. These are all in the halide group. Or halide, halogen?
halide.
Halide?
Yeah.
Okay, halide group. So, you know the one column that's right before the noble gases? Ooh, these ones are so close, but not quite there yet. They're halogens. Okay, look, like I said, everything sounds so similar. So they're all halogens, right? So anytime you see a halogen, you know you're weak base, strong nuke. So, and then the last category, the first one, strong base, weak nuke, DBN and DBU, I feel like they stick out because, like, low-key, what is that? Like, it's totally fine. I don't expect you to because they're not atoms. They're not like common compounds. They're like larger synthetic compounds. Like if you look up their structure, ugly, nasty structure. So they kind of stick out because they don't look like anything else in the chart. Like anytime I see anything that starts with D, I'm like, wonder what that could be. It's gonna be category 1 every single time. So trying to find those patterns within the chart itself is going to be super helpful. And then a really good way is also like just flashcards, making some flashcards of these and memorizing them, because that's definitely going to be something that you need to know off the cuff for an exam. Any questions about those?
I'm searching in the textbook, for the figures, but they're not popping out.
No.
No,
7.17.
7.17, 7.
Scroll through chapter 7. It's tedious, but you'll find it eventually. Sometimes when you try and control F the textbook, it doesn't like it because certain things are like in a different font or they have like weird spaces in between them, or they'll put like a random period and it'll be like, oh, that doesn't exist. So
I'm trying to determine whether differentiate this strong base and weak base. Am I looking at the probability of like accepting hydrogen or?
yes, strong nucleophile versus weak base weak nucleophile is what you're looking at. So basically, anytime you have an oxygen with a negative charge, you're going to be in strong base strong nucleophile. Anytime you have the oxygen and it's got like all its bonds filled, or it's got like double hydrogened up, yeah, that's gonna be weak weak. Okay, sweet. Go ahead and move on to the next slide. So put it all together. Here's an example of a question that you might see. And I based this one off of like, I think it's like an old, like really old ancient exam question. Don't want to out my age here, but from when I was taking the class. So it says determine your reagent's basicity and nucleophilicity is going to be step 1. So if we're looking at this problem, you have your material. So that's like this bromine that's like kind of like sitting on the left-hand side of the arrow. Imagine it's like what's already in your beaker, okay? And then your NaCl, that's going to be what you're pouring in to your beaker. So step 1 is figure out NaCl, what is that? And if we remember that Cl is a strong base or weak base strong nucleophile. It's our halogen group. The other thing I see people get tripped up on so often is they will see the Na and they'll be like, what is he doing there? I don't remember this reagent at all. Luckily, does anybody know what Na is? Uh, Salt. He's just there to stabilize the compound. He's not doing anything. We call those spectator ions. So what they'll do is they'll confuse students a lot because they'll be like, I remembered Cl. I didn't memorize NaCl. He's not doing anything. He's just sitting there. You can ignore him. So keep that in mind whenever you see Na tacked on to something. Okie dokie. So now that we know it's a weak base, strong nucleophile, let's figure out how substituted is your halide. So does anybody remember from like resonance or maybe the acid base chapter, how do we determine how substituted something is? That's good. Sure. So what do is we're going to look at the carbon that is attached to our our halogen. So if we're looking at the bromine, we're going to look at where's my mouse? Please, I keep losing it. Well, we're going to be looking at the carbon that is right beneath the bromine. So once we have identified that carbon, our next step is to figure out how many things other than the bromine are attached to it. So I'll throw that open to you guys. How many things other than the bromine are attached to that carbon? Well, we count like the chain as like just one group.
Methyl and then hydrogen atom. Where we what's connected to the carbon and
Yes. And I'll say you don't usually count hydrogens.
propyl and methyl.
So we would say that that is secondary substituted. We ignore hydrogen, they're itty bitty. They don't, basically, when we're figuring out how substituted something is, we're trying to figure out how bulky is it? How much junk does it got on it? And so we don't really care about hydrogens as much because they're tiny. They're not really getting in the way of any reactions. So if we're looking at this carbon right here, and we don't count the bromine, then we have this group to the left and this group to the right. And so that's going to be tertiary substituted.
You said, wait, you said. I thought you said the second.
Sorry, secondary. My bad. That was just me misspeaking. Secondary.
So when it comes to the second substituted, you only like look at like maybe just methyls or ethyls.
Yeah, okay. Ethyls, ethyls.
What about if there's a chance where it's like a chlorine or something like?
Like a hetero atom, so like chlorine, bromine, oxygen, you would count that as well.
I would
Basically, the only one that you're not counting is hydrogen.
so just ignore the hydrogen.
Yeah, just ignore the hydrogens, which should be easy because they're not even drawn there anyway. So they're super easy to ignore. Basically, anything you can see, excluding the halogen, because the halogen, like this bond, is kind of what we're assessing. Okay. So now we know we assessed that the NaCl was a weak base and a strong nucleophile, and we determined that our original starting product was secondary. So we can follow that to the like coordinates, and we determine that what reaction is going to happen here is an SN2 reaction, just an SN2 reaction. Does that make sense of how we use that chart?
Um, um, is the, is this the bromine something?
It's just color coded, like all the SN2s they put in the blue and stuff like that, just to like color coordinate.
Okay, and I'm assuming that if it's secondary strong base, strong nucleophile, would it be like most likely E2?
Yes, I'm glad you asked. So, just in case people online didn't hear the question, we were saying if we had a strong base, strong nucleophile at secondary, what does this mean? So, this means that your E2 is going to be your major product and the SN2 is going to be the minor. And so, that's where making sure that you're paying real close attention to how professors phrase the question is going to be important because sometimes they'll say, write the products as like a free response. And a lot of people will write the major product, but not the minor product. So you got to be careful for that.
So the minor product of this is SN2.
Yes, the minor product would be through SN2.
Major.
Um,
Sorry, major.
question we did before, the major one would be SN2. Perfect. Questions on the breakdown of that example and how we use the chart to figure out what mechanism we would be using.
And also, I looked in the textbook, the figure number actually changed.
Making me feel so old now. Back in my day, it used to be 7.18.
I screenshot it. It's now figure 7.22.
Oh
Yeah.
my god. This isn't even funny. Okay, guys, for anybody online, apparently the numbers has been changed and it is no longer figure 7.18, it is figure 7.22.
Just for the other one too.
It's usually paired with that one, so it should be in the same general area.
Wow. It's also real, yes. Second degree. Good, so.
Exhausting.
The weak base, weak nucleophile with the second degree is filled with the.
Weak base, weak nucleophile, second degree. Are they inventing new chemistry on me, bro? What is this? Okay. Oh, we got a message in the chat. Got it, thank you. Okay, perfect. Okay. So our final answer for that question was SN2 mechanism will occur as the only product. And again, if you want to consult the updated version of the textbook, apparently that's how long I've been doing Orgo, is now they're making new Orgo on me. So, okay. So other reactions, all the other chapters, because that'll get us through chapter 7, but like what about chapter 8, 9, and 10? So I know, looking ahead, but no need to worry because you can always come back to these 3 guiding questions. And this is how I would kind of make my study guides in the class. So anytime you're coming across a new reaction or a new reagent, is question number 1, what is the stereospecificity? That's a fancy word. But what it comes down to is, are the molecules being added in a certain configuration, as in like cis or trans? So you guys recently had that chapter on like enantiomers, diastamers, stuff like that. So that's what it's asking. Like in space, are the molecules being added a certain way? The next question you're going to ask is there regioselectivity? And so it's like the molecules being oriented in space. That refers to, is there a particular spot on the molecule that is going to be preferred? And so when you go through the chapter, you'll learn fancy terms for it, which is like Markovnikov or anti-Markovnikov. You don't need to know what that means right now. You just need to ask yourself, is it being added to a particular spot? Lastly, rearrangement. So, last question you want to ask yourself is, will it be able to go through rearrangement? So we have an example here. You have a methyl, and it's going to move on over to that carbocation to stabilize it, because it goes from being a secondary carbocation to a tertiary carbocation.
Okay, that makes sense. So it's just the bond that it's just arrangement.
Yes, it's just rearranging within itself.
Okay.
Some reshuffling, some spring cleaning. These 3 questions are going to be relevant to any of the new reagents that you're learning. So as long as you know these 3, you'll be set, right? And that's usually how I'll set up my study guides, is on one side I'll have the reagent and the product that it gives, and then on the other side I'll have bullets about stereospecificity, regioselectivity, and rearrangement. Trying to think if there's anything else I want to say. Oh, very important to know these 3 as well, because you'll have a lot of examples where they have very similar outcomes, but maybe one is regioselective and the other one isn't. And so professors love that because it's ripe for like trick questions on exams. So knowing these minor differences is going to be super, super important to making sure that you're not getting tripped up on the exams. Does that make sense? Sweet. Okie Go back to your definitions and break down the material as much as possible. Because at the end of the day, it all comes back to nucleophile and electrophiles and those 4 arrow pushing methods. Make sense? Sweet. Yippee. Okay, so activity, it was gonna be Kahoot, but then I realized that I'm actually so old that we stopped having Kahoot now. We don't pay for it anymore. So, I still have Kahoot, but we're gonna treat it like a presentation instead of like you can still join it, but I can still show the problems up on the board.
Buy on Kahoots. They're not free. I don't think.
No, unfortunately, if you have like free Kahoot, you can only have 3 people join. Yeah. Yeah, so that's on the podium. But non-bonus is we have 7 people online who would be excluded, unfortunately. So we're gonna treat it more like presentation style instead. And we'll imagine the Kahoot music in our hearts. So, oh my God. Sorry, I looked at the time and it jump scared me a little bit. Okay. Presentation style. I can't even look at a presentation. Okay. Please, Kahoot. Please.
You can send the link in the chat and we'll do like.
That's true. I could send the Let's start without any. Okay, well, there, we'll just start it. So we got true or false, the oxygen is acting as a nucleophile. And I don't think it's on a timer. I think I put it in presentation mode. Oh, it still plays the music. Okay, that's actually, I'm gonna mute it because why is it so intense? That's scaring me. So here's a little example. Hopefully it doesn't flash the answer. True or false, the oxygen below is acting as a nucleophile. Nice. Look, who has like a vendetta against me?
There's another negative charge on the oxygen, and then another positive.
It doesn't have a positive charge. Yeah, so that would be false because positive charge is going to be electrophile. It's looking for those electrons. So I guess now that we know that it actually, wait, can I change it in settings? What if I don't want it to time us, please? Oh, that's actually not an option. It says you will be timed. Okay, guys, well, we're gonna have to be really speedy with our reactions now. Okay. Um, oh, this one's more just, did you remember like the study tip stuff? So what are the multiple choice questions at the end of the textbook called? The alcohol style questions, yeah. Okay, okay, let's check our chat. Yes, ACS style, perf. And please remember your final exam, it might be worth taking a gander at those. Okie dokie. Okay, well now how do I go to the next slide? Please, Kahoot. Yay. So, okay, here's an example of an arrow pushing method. So, what arrow pushing method do we think is happening here?
Matter.
Yeah, for our people online, you can put it in chat. Or nucleophilic attack. Okay, one vote for nucleophilic. Okay, let's consult the chat. Let's consult chat. We'll phone a friend. You- Okay, so I can see how you thought it was. I can see how you thought it was nuclear or rearrangement, right? But in rearrangement, like there's no addition of bonds. Like there's still the same amount of bonds as
Yeah.
before. It's just the location of the bond is moving.
Just people feel like it's have to be like an extra,
It creates a new bond.
and like just rearrangement, same bond, say. For a bond or something.
Yes. We're losing daylight, so I'm not sure how many more of these we'll get through. So, what's the name of the chart that shows you which mechanism to use? Who now we know has a different name, so actually all of these are wrong. So I think we can kind of skip this one because Loki. Oh, who said you're not skipping it? You will sit here for 10 minutes. That might be her dead name now. She's going by 7.22 now. So we'll see. Okay, okay. We got another arrow pushing method. So what arrow pushing method do we think this one is? Oh, we got proton transfer. Mm, Cos'era? Cos'era? Anybody? Anybody? Oh, oh. Consult the our people online. Yeah, I actually did trick you guys with that one. So basically, the reason I picked this one is because it's something people get tripped up on a lot. Proton transfer is between two separate molecules. Carbocation rearrangement, again, within the same molecule. So important to know. Proton transfer, two separate.
I was genuinely thinking, wait, maybe it could be carbon data.
Yes, yes. Okay. Gonna do one more problem. We probably won't get through all of these because we are at time, but we'll do one more for the road. Unless it's a goofy one. No, no. So, as our final question, what guiding questions can help you classify your reagents? Yes, that's crazy. Look, if all of the above is an option, it's probably going to be all of the above. So let's see what chat is saying. Yes, all of the above. Good job, good job. Okay, sweet. That kind of gets you introduced to some of the more complicated arrow pushing methods. So if that tripped you up, don't worry too much about it. Again, you haven't even seen this content in class yet. I did literally just tell you guys about it. You learned about it today. So don't be too concerned, but hopefully this helps you get a guide of how to better use your study time, how to read the textbook, how to approach that, and how to start thinking about those mechanisms and all those reagents. So with that, for my people online, we are coming to time. So did any of you guys have any final questions before I go ahead and end the Zoom? Where did the Zoom go? Oh, there it is. Oh,
Thanks as you're sharing your screen.
oh, stop sharing. Yay, yippee, yippee. Okay, not for now. Thank you. No, thank you so much. Of course, of course. So I really hope this helps you guys going into your next exam. And just remember, you guys are in Orgo. I know it's tough stuff, but you've stuck it out this far and you guys got this. Good luck on your next exam. And I'm gonna go ahead and end it on the Zoom end. Bye.